Perception's technology uses
基于覆盖酒店内全场景的客人身份识别，在无感梯控里通过刷脸就能自动识别到达的楼层。
然后这个张松老师的介绍我也是听不见的。
您可以这样，如果你想分享，我这边是登了一个账号，也是放了那个。
王总，你能听到吗？我可以听到你啊。喂，我可以听到。
张老师，我 OK 了。
好。你把你的摄像头打开吧。
这个张松老师的介绍我也是听不见的。
您可以这样，如果你想分享，我这边是登了一个账号，也是放了那个。
OK， 王总，你能听到吗？我可以听到你啊，可以看到啊。
OK。
那我们现在开始，要不？喂，我可以听到。
张老师，我 OK 了。
好。
OK，
你把你的摄像头打开吧。So it is 9 o'clock now. So we will get a second day conference start. Good morning, good afternoon, or good evening. It depends on where you are, of course. So it is my greatest honor today to introduce one of my best friends, to start today's program. We were both young when we first met. Now I'm old, but he's still very young because he was born after the 1980s, and I was born before that. Nevertheless, we have the same love in 3D sensing technologies, and we share the same desire and passion to advance the 3D world, though, of course, from different perspectives. Dr. Huang is the world leader in 3D vision field with over 17 years of experiences. He published numerous papers and presided several international conferences. He received his bachelor degree in mechanical engineering from Peking University and spent more than 10 years in several countries pursuing his graduate studies and postdoctoral trainings. His broader research interests include Fringe Projection, laser interferometry, computer vision, photogrammetry, holography, spectral correlation, visual thermal, remote sensing, and microscopy. In 2013, he returned to China and founded Orbec. That company has emerged as a global leader in 3D sensing technologies. Orbec becomes the Asian's top 3D sensing one-stop shop solution provider. At its latest round of pre-IPO financing, Orbec's value surpassed $2 billion. Orbec has renowned financial and strategical investors, including Ant Financial, Hair, MediaTek, and Shanghai Advanced Institute of Finance. Dr. Huang has won numerous awards. It will take me the entire hour if I want to list all of them today. So I just point out the most recent one. Earlier this year, he was selected as one of the 40 people who have made the most influential contribution to the Shenzhen Special Economic Zone over the past 40 years. Last Wednesday, actually just a few days before, he was invited to attend the celebration of the 40th anniversary of the establishment of the Shenzhen Special Economic Zone. Today, Dr. Huang will give a plenary talk to share the industrial and consumer 3D sensing, silicon, cloud, and applications. He will leave enough time for your audience to ask questions. He also brought his Vice President, Dr. Zhi Chen, with him during the question and answer session. So with this, I will turn this stage to Dr. Huang. Welcome, Dr. Huang.
Thank you, Professor Zhang, for your nice introduction. Good morning or good afternoon, professors and students. It's my great pleasure to talk with you. Actually, after I found Orbec in 2013, I never give academic conference, never. So for last 7 to 8 years, I didn't do any like presentation like today. So today, I would like to share with you my experience, and because we are starting from industrial and then getting into consumer 3D sensing. So to get into consumer 3D sensing, we need a lot of more development because industrial, we focus on accuracy. We don't care about the price. We don't care about the bulky equipment. But in consumer, the price need to be very low and the reliability and everything change. So the topic today, I will going to talk with silicon. We need to go deep into silicon, and then we need to supply cloud solution to our end user, and then I will introduce more application of our 3D sensing. So I think 3D sensing, everybody knows what it is. The world is 3D, but most of the time, the camera capture only 2D image with RGB information. So here you can see that with 3D sensing, we can capture the 3D human face. We can have a 3D model of your dining room, everything. So you can hear a lot of words like digital cyber words, digital twin, or AR mirror world. All these words is talking about 3D sensing. We digitize the whole world into 3D. And this is the virtual world. And this virtual world can provide more information to human being and can interact with human being better. This is the future life. So 3D sensing is very important now. So here I show you some of the industrial application and equipment we developed before. And all back we have a sub company focusing on industrial application. So the left one is the 3D scanning system, and the middle one is also 3D scanning, but he focused on the pipeline inspection. So for irregular pipeline, it's difficult to inspect whether or not the accuracy, the pipeline is right. So using non-contact optical method, we can do the measurement. And the right one is the deformation measurement to measure the use DIC to measure the deformation and stress strain. So here I give a very quick introduction of these three products. So I think the principle you know very well, but to make this principle into a product take a lot of time, very long time. So this is our product. Now you can see that this one can scan some mechanical part with very, very high accuracy, up to 10 micron. So this is the traditional fringe projection and phase shifting method. I think everybody knows this. But to make equipment suitable for industrial take more time, and also the software, a lot of things. So this is the one model we create. We can measure up to 10 micron. And here, next one, skip it. The next one, this is the equipment, very bulky, and its weight is about like 600 kilogram. And this bulky thing, we will put the pipeline into it, and it can measure in several seconds the 3D shape of it, and compare to your design CAD data, you can know that okay, whether or not this pipeline is correct. This regular pipeline was widely applied in like cars, in like refrigerator, a lot of home appliances. So the next one, digital image correlation, and you can see that I quickly drop here. The equipment is like this, and you can measure the surface deformation, stress, and strain. I think in mechanics, this is important equipment. So this is our background, but we also developed some laser interferometry equipment for non-contact some discussion, but we didn't show it here. So this is our background. We start from academic. We know a lot of like mathematics and optical measure, and then we develop industrial equipment. But later we found that the consumer market is much bigger, and the influence may be much bigger because industrial maybe the price is like tens of thousands of dollars on equipment, but the volume is very small. So here you can see that now is Internet of Things. Internet of Things. In 2020, in the world, we have over 20 billion smart devices connected to Internet. So this is very huge volume. And the Internet of Things, the smart device, they will eventually need a human being eyes. They need an eye. They need vision system to see the world better, to understand the world better. So we see this is much bigger opportunity. And you can see that in 2017, when Apple launched its iPhone 10, iPhone 10 is embedded with 3D sensor. So the market is going up. And here you can see that in 2017, the 3D image market size is very small. It's only $2 billion. But in 2023, it will be $18 billion. And I believe that in the next 10 to 20 years, this 3D sensing market will continue to grow with very fast, with very high speed. So here's some research about the market size of like smartphones, like smart post terminal, and smart lock, smart door, or smart security device, AR, VR, smart robot. You can see that even for smart home, smart phone only, they expect to exceed the number of 10 is like 1 billion set unit in 2023. But I think with the COVID-19, I think this will be delayed for 1 to 2 years. But anyway, the market is very, very big. So for OBEC, we see this opportunity before Apple launched its iPhone 10. So we start our company in 2013 January, and then in 2015 we tap out our first ASIC chip with like structural algorithm embedded into the ASIC chip. So now we have 4 R&D center. We have like over 800 staff, and more than 70% of the staff are R&D team. And we have filed 800 patents, and over 250 of the patents have been approved. And over the world, we have more than 3,000 now actually global customer. And the volume we ship out 3D sensor is more than 3 million. This I think except Apple and Huawei, the world number 3 is up. So this is some of our product. You can see that the very traditional 3D sensing camera Ultra Pro, and this one looks like PlumSense. The PlumSense camera is bulky, very big, and then we developed much smaller one. You can see the HRP. The thickness is less than 6 millimeter. 6 millimeter, very, very thin, and the length is only less than 40 millimeter, and the width is also 7 millimeter, something like that. So this HRP can be embedded into smartphone, very small size. So this one is the world's number 2 3D sensor embedded into smartphone. Is you can see it in 5S, Oppo 5S smartphone. So this one is the HP computer, desktop computer, embedded with all-back 3D sensor, and you can scan like a suit in 3D model. You can create a 3D model in 10 seconds. And also you can see that the 3D facial payment equipment and industrial scanner, 3D scanner, at least D2 plus, it can work inside the dining room or outdoor with under sunlight. And here is the 3D camera for industrial robotics. They embedded all-back 3D sensor, and a lot of robotic company in China and all over the world, they embed all-back camera in their robotic arm. So here is the technology we have developed and we are developing. You can see that here, structure line and stereoscopy, and top actually we have Itop, we have Itop, and LiDAR, and we developing array sensing LiDAR, not a single dot LiDAR. We developing array sensing LiDAR. So we have 5 kind of 3D sensing technology. But as you know, 3D sensing is very new. It started from 2017. It's only 3 years old. So just like Huawei, when Huawei started a company in 1980s, at that time, the telecom industry is very new. Everything is new. So everything Huawei need to do it by themselves. So for 3D sensing, the field, consumer 3D sensing is new. We need to do everything. For example, now the laser we use is from, they are specially designed for not 3D sensing, but for telecom. So the frequency is very high, but the peak power is not so high. So for laser, if we want to do 3D sensing better, we need to do much more work to customize the laser, to develop sometimes develop new technology, new material. So for example, for the sensor, structural sensor, we can use off-the-shelf, but off-the-shelf sensor is not so good. We 3D sensing, we know a lot of new things. So all-back, if we want to do 3D sensing better, we need to go very deep into silicon. For sensor, structural line, for Itop, for Itop, and for stereoscopy sensor, for laser, for nano optics, we need to develop our own component, which is specially designed for 3D sensing. So this is why we say we going deep into silicon. And also we need to develop some algorithm embedded in the ASIC chip to calculate depth information in much faster speed. Yeah. So we go into deep into silicon, nano optics, and we go build our own module, and we build our 5 kind of 3D sensor. But industrial, how to use this 3D sensor to make their application better. So we also need to develop our own SDK, and we provide total solution for different industrial. For example, cell phone industrial, for like face recognition industrial, for car industrial, and for like surveillance industrial. We need to provide total solution to them. So we need a lot of algorithm, and we need to provide a 3D AI cloud to them. So this is what we do. Actually, we don't want to do so much things, but this is new field. If you want to provide best solution to your end user, to your customer, you need to do more. So we are the only company in the world that we covers 5 types of major 3D sensing technology, and we go deep into silicon, and we also provide cloud solution. Cloud solution now we are still under development. We will provide the cloud solution very soon. And 3D sensor, as you see, they have like laser emitter, laser module, micro optics, and then the sensor and ASIC chip and algorithm, a lot of things. So this is the cross-disciplinary merger of a lot of academic field, including optical, mechanical, electrical, and also ASIC chip design and sensor design and algorithm, SDK, and firmware, a lot of work together. So we learn a lot. We learn a lot from this 7 to 8 years of starting the company. We learned a lot. Before, I mainly know some algorithm, optical things, but now, okay, the whole industrial, even the foundry, like TSMC, like TowerJet, we know it very well because we very closely work with them. So this is the thing we need to do very good in order to be #1 in the world in 3D sensing. So this is some of the chip we have tapped out and provided to our customer. These 4 chips are all for structural algorithm, embedded structural algorithm. And you can see that from SMIC to TSMC and from 55 nanometer to 28 nanometer, and next one maybe we will go even high-end solution. So, and the capability of the chip is continuing increasing. And this is something that we didn't publish yet. So this is our Itop depth engine, and we can using this Itop sensing for AR ruler, for AR night vision, and AR blurring. The Chinese cell phone company called Meizu have been using OBEC depth engine for their Itop solution. And we have also some new solution you haven't seen on cell phone yet. This is we call it the enhanced Itop. You can see that the right column here, normal Itop are affected by the reflectivity of the object surface. So the depth information will change if the surface color is different. And also at inner right angle, you can see that the Itop depth data is changed. There are a lot of noise, multiple path problem. So we have this enhanced Itop solution. You can see that the surface emissive reflectivity will be eliminated, and also the inner corner you see very good. So this enhanced Itop solution is very close to Apple's Itop solution. So we are developing enhanced Itop. Also, we are also developing kind of Itop solution. So this is the under display structuralized solution. So Apple now have structuralized sensor embedded in their cell phone, but you can see that their screen is not full screen. In China, a lot of cell phone companies they want full screen. The full screen looks more beautiful. But how to embed the sensor under the screen? The screen can display, but the 3D sensor can still work. So we develop some under display screen structuralized solution. So this is the experiment result. You can see that the accuracy is very good, but so far this solution can work indoor, but for outdoor under strong sunlight, it's still not very good. So we are still working hard to improve the outdoor performance. So this is something that combine passive stereoscopy algorithm and active one. We project the random dot to the space, and we use like stereoscopy algorithm and improve it. And you can see that the result is quite promising. So the left column here is the scene, natural scene, and the middle column here is the current best solution of the cell. You can buy some stereoscopy 3D camera from all over the world, some big company, and current the best solution, the best result is the middle column. But OBEC, recently we developed a combined passive and active one, and we modify and improve the algorithm, and you can see that the depth map is much better. But this one actually I shouldn't show it because this one will only off the shelf from Orbeck portfolio 3D camera in next year, maybe middle next year. I'll just show some algorithm result here. And now we call it NPU or AI chip is very hot topic. Most AI chip now they mostly work with the RGB 2D image. So Orbeck, we are specialized in 3D, so we can generate the best 3D data. So if we use 3D data properly, then the face recognition and all the skeleton checking, a lot of algorithm can be improved. It can be better than only 2D data. So Orbeck, we developed some special NPU, and this NPU work with Orbeck 3D data and will give you a better result. So we have our own AI chip, but specialized for 3D data. So our next chip will be like they is capable to deliver 3D information. We embedded 3D IP inside it, or Itop, active and passive stereo, structural embedded into it, and then we embedded our home design NPU AI chip, and we also have RISC-V core CPU, and also our chip will before the chip is tapped out, we will apply a lot of application algorithm. For example, 3D skeleton checking, and then we see whether or not there is some bottleneck, some of it, and we optimize it. So our 3D AIoT chip will tap out next year, and this one is the world's #1, specially designed for 3D data, and I hope it will be much better than 2D one. And this is some of our other algorithm. This is the 3D body scanning. You can see the 3D body scanning here, and a lot of like soup brand buy our equipment to scan their foot, scan their human body. And this is the large scale 3D reconstruction and also the small scale one. So 3D technology, they have a lot of application. So next I will introduce a lot of application, and all these application is Orbeck customer using Orbeck 3D sensor, and they develop their application. So here, the #1 you can see Oppo 5X, the smartphone. The smartphone we embed with Orbeck 3D sensor, very small sensor. You can see here, very small one. And this one you can scan your 3D face and unlock your smartphone. And this one is the full screen. And this is the world #2. World #1 is iPhone 10. World #2 is Oppo. And we launched this 5S in May 2018, and Huawei launched their 3D phone in October or November 2018, 5 or 6 months after Orbeck. And this is the nice application we work with Ant Financial. So now you can scan your face to pay. You don't need to bring your cell phone. You don't need to bring your wallet. You can pay. Or when you go to hospital, you don't need your ID card. So you just scan your face. You can check in and you can do the payment. So we can a lot of application. If you need your identity, the merchandise need to identify your identity, then you can use your face. You don't need to use other ID card, something like that. So this is another application our customer use object sensor, and here you can scan the food and then recognize, okay, this is vegetable, this is meat, and then generate the menu automatically, and then okay, this is a $10, and then can scan the face to get paid. So very easy, very easy. And this is the in subway 3D face recognition turnstile. So when you calling, when you doing, yeah, so you just go through, scan your face and just go through. Very familiar. So not only subway, now bus are going to adapt this kind of 3D face recognition. And this is the digital lock. So digital lock originally using password, and then they're using fingerprint. And now the most advanced digital lock, they're using face recognition. And 3D face is very nice working with them. And this is smart retail. If you equip your shop with some 3D sensor, so you can analyze the shopping better, the shopper better. Okay, so Howard, you like milk, you like what? You better, and also they can recognize what merchant, what goods you have, and do the payment by facial scanning. And this is the future. This future is humanless smart hotel. So you don't have a counter. You just put your hotel room with your cell phone, and then you go directly to the lift, and the lift recognize you. Okay, go to a story, and then you stop, and then you can unlock your room with your face. So it's much more convenient. But now it's just some demo. It's not a real one. But I think maybe 3 to 5 years you will come to realize. Yeah. So this is realized already. The left one is in hotel, and the right one is some restaurant in China. And in restaurant or in hotel, the robot equipped with the sensor, 3D sensor, they can build a 3D map and then localization themselves, and then they can navigate to any position they want, and then to serve people better. Now, one of the robot price is like 50 to 100K Chinese yuan in China, but they say it works as good as one employee, one person, so it is not that expensive. And here is the warehouse robot. In warehouse, robot equipped with 3D sensor, they can navigate itself and do job by themselves. They can avoid any obstacles automatically. And here is the DMS, the driver monitoring system. So driver safety is very important. So when the driver is young, is like sleepy, and then the system need to remind you, alarm, okay, be careful, be careful. Or when the driver is using phone or looking around and small, they need to alarm. Actually, 2D camera can also do this DMS system, but 3D camera is much more robust. For example, if you use 2D camera, you alarm 100 times, maybe 20 times is a wrong alarm. It's not accurate, wrong alarm. But if you use 3D system, 100 times, maybe less than 5 times is wrong alarm. So this user experience is better. And here is the, the baker, the largest house ranking and selling platform in China, largest one. And this platform use object 3D sensor to scan 3D home. And so you don't need to go to the physically go to tech home. You can see the 3D structure, everything from internet. And also Metapod in US Metapod also use object sensor for 3D home scanning. And this is the smart home. So this is kind of like just like Connect game, Microsoft Connect game, and also the right one is the interactive. It is like touch screen, simulated touch screen, interactive dining room, interactive games, something like that. So in smart living room, we can care the elderly people. This is kind of the surveillance. If elderly people fall down, they can alarm automatically, and it prevent your something like that. Yeah. So education, sports fitness, as smart kitchen, a lot of application. And this is the virtual fitting room. 3D sensor can scan your 3D body and also can virtually fit clothes on your body. And before you buy the clothes, you can see what it is on you. So you can also like show it to your friend with WeChat, and then okay, if a lot of people say very nice, then you buy it. If they say oh ugly, so you just ignore it. So this is the in logistic industrial. So if you want to measure the area, the bulk of this object, you use 3D sensor. It's much easier. So Optical will work with a few top company in this field and give them just something like this, a smartphone, but with 3D capability, can measure the volume much easier. So this also interactive projector, and you can do all kinds of applications. Okay, so this is all our customers can actually human have 3D vision, but smart device so far they don't have. So we believe that smart device in the future, they will have better vision capability than human being. And then from high-end smart device to middle to low-end, they will gradually embed it with 3D sensor. So a lot of industrial area, smart home, like smart city, smart security, smart vehicle, robotics, industrial, house scanning, mobile and AR VR, smart logistics. I think all this industrial now they have already applied 3D sensor already. But I think in the future more will apply 3D sensor. In the future we call it this is AI era, AI world. But if a robot want to be more intelligent than human being, their vision capability need to be better than human being. So we do 3D sensing, and we also develop some like AI algorithm as well. So I think 3D 20 years ago, 18 years ago, when I start my research work in 3D sensing, at that time 3D is not very hot actually. So for 3D paper, we write a paper with 3D algorithm. Normally the impact factor is very low, below 1, or the best one maybe impact factor is 3. But for that for chemistry, for like bio, or for like something nano, the impact factor is kind of like 10, 20, 30 natural science. But for 3D sensing, it's kind of industrial work. It's kind of like not so hot area. So at the time, I'm not so happy because we are not the mainstream. But in 2017, when Apple launched its iPhone 10, and then 3D sensor into cell phone and into iPad, and the data will into more and more smart device. I think 3D sensing will really change the world in the future. So for students who are working with 3D sensing, I think this is your spring. Your spring is coming. Your spring is coming. So OBEC, we are born. Our gene is 3D. So we will, for the next 10, 20, 30 years, we will work in 3D. We want to be the world number one in 3D sensing from silicon to cloud. So if professors and students, if you are interested in collaboration with or joint project with OBEC, or if students you want to join in OBEC for a 3D journal, then welcome to send us email, and we welcome any kind of collaboration. Thank you very much. So if you have any question, Dr. Zhe, we can answer you. Thank you.
Okay, thank you, Dr. Huang, for your kind introduction about the OBEC and all the great work your company has been able to accomplish within 7 years. That was very, very impressive. So, I have certainly have a lot of questions. So maybe I ask you kind of philosophy question, right? So since you are so successful in this field, what advice you would like to give the younger generation? So you are really young, but I'm talking about the younger generation, right? So what kind of advice you are going to give them to hopefully they will be as successful as you are in when they become a little bit older. So
okay. So I'm not so successful. I'm not so successful. We are just starting. So far we are okay, but I think the most important factor is that this era we enter this field in the right moment, and now we have a very good position in this industrial. We are number one in China in 3D sensing, and I believe that in next 3 to 5 years we may be number one in the world in 3D sensing in all kinds of these 5 kind of technology. So we cannot say successful, but we have a good position here. And for advice for younger generation, I think for this younger generation, students are much more intelligent, much more smart than us before. They know more. But I think one thing the students need to remember that you need to select one field, or if you want to go to academic, okay, do it 10 years, 20 years. And if you're going to industrial, select one direction and go deep, 10 years, go very deep into it. This is very, very important. So for example, I have been in this 3D field for 18 years. And if I enter this field 5 years, 2002, I entered this field. If I left this field 2007, 5 years after that, then I will be nobody. But I entered this one 10 years, and 2017, I established a company. At that time, maybe the algorithm, the optical system, everything we know, because we spent 10 years, then we know it very well, and then we have more chance to open a better world. So focus on one of the promising field and spend 10 years into it. You will be much better. Then you change several times within these 10 years. And this is my advice.
Thank you. That's great advice. So basically, what you try to give the young generation is that if they are interested in something, even though some area may not be very hot at that point, they should continue work on that and go deep. And after a while, so the moment could come, and if they grasp it, hopefully they will be as successful as you are. So
much better than me.
So you are the role model in this field. So there are quite a number of questions, maybe a little bit technical questions from the audience. So the first one is about the what is actually the biggest challenge in the field right now.
Okay, so Dr. Zhi answer this question or?
Sure. Yeah, I will take over the Q&A session now.
Okay.
Yeah, so I'm Chen Zhi from OBEC. I will answer the questions in the Q&A session. So the first question is about what's the biggest challenge in the field, right, yeah. Professor?
This comes from the audience, so.
Sure. Yeah. I think that's a very big question. It's about asking the biggest challenge. So. In my view, for this 3D sensing, I think it's not about technologies. As when we want to transfer technology into our commercial field or in our everyday applications, we need to think about what's the application and what is how should we adapt the technology. So I think the biggest challenge is the gap between the science, the R&D world and the real life world. So we need to transfer technology into application and we need to make it valuable for the people who want to use it. So I think that's my answer.
Okay, yeah. So this is basic, it's not just about technology. Technology itself is not enough, right? That's what you're trying to
say.
There
are a lot of things involved in the commercialization process. So it's not about technology. It's all about focusing on people and how to make how to make a value from the technology for people.
Yeah, I completely agree. So I think
maybe I can
go ahead.
I can add something to this answer. So I can see that in terms of technology, we faced a lot of challenge, very difficult. And as Zhi says, technology itself, even we have very good technology itself is not enough because the good technology to application to product is a long way to go, very long way to go. Like 100 technology, maybe only one can go to real world. So in terms of technology, you know that in the end, robot computer vision will be better than human being vision, human eyes. But so far, they are not as good as human eye. It's still a long way to go. So for example, so I think this field is just started. We still need like 20 years to develop this five kind of 3D sensing technology to meet the requirement of like robot. For example, the LiDAR. LiDAR now is scanning LiDAR. It's rotating scanning LiDAR. And the depth map is very sparse. It's not dense. So, and also the LiDAR equipment is very bulky. Yeah. And the line now is using most of these use the 905 nanometer. This is kind of not very safe for human eyes. So for LiDAR, we'll just give an example. A lot of things need to do. We need to later, in the end, we need to develop very small size, very cheap, and array sensing LiDAR, just like camera. We snap, and then we get the whole array 3D information, not by scanning, because scanning, rotating equipment, you cannot embed it into every car. It's just, you can embed it into some taxi, but not your home car. So we need to make smaller, cheaper array sensing, and then reliability need to be better. Now, the LiDAR, normally you work for half a year, 6 months, you need to change the LiDAR because the reliability problem. So a lot of things very difficult. And to make such the best LiDAR, maybe you need to change wavelength. You need to change wavelength from 905 to maybe 1550 or even longer wavelengths. And if you change wavelength, the light source need to be changed, and the receiver, the sensor need to be changed, because silicon is not sensitive to wavelengths bigger than 1 millimeter. Not 1 millimeter, 1 micron. That's 1,000 nanometer. So we need to develop some new kind of material to sense the longer wavelength optics. And if you change the material, foundry, the process of the foundry need to change. The doping, the equipment, everything needs to change. So I can see that in terms of technology, we still have 20 years to go, 20 years at least to go. And in terms of even you have very good technology, from technology to product is very, very long way. For example, in industrial, the scanner, we can scan very, very accurate, 10 micron accuracy, but the price is like tens of thousands of dollars. But cell phone, less than $10, you need very good sensor, 3D sensor, but the volume is like 1 billion volume, something like that. So from technology, you to customize every component, every algorithm into ASIC chip, and then to like large volume, low price, and then to consumer application is very, very, very long way. And even giving another example, for cell phone, if you want to get the test map, maybe not that difficult. The algorithm, the principle is there already. But you know that the cell phone, they use the cell phone, maybe they can drop the cell phone from like 2 meters high to the ground, and the cell phone may change a little bit. And the emitter, laser emitter, and the receiver of the laser, the optical axis may change for 1 degree or 0.5 degree. This is a very small change. But even you change 0.5 degree, then the 3D information, depth information will change for maybe 5%, 10%. So this is not acceptable for Apple, for Oppo, for cell phone company. They say that, okay, your 3D sensor need to work under any situation. You need to work. The accuracy need to keep the same. So how to make it after the optical axis change, how to make it still work? So this is need a lot of research work, algorithm development, and also for cell phone, you need high humidity, high temperature, low temperature, a lot of things. So much more difficult than a demo. A real product is much more difficult than a demo. So just to share with you, it's the long journey actually. But I think it's very proud that to see that people use your product. You can see that, okay, the facial recognition for payment, oh, they use my product. Your cell phone use my product. Very proud that this, I think, is our value. If it's not that difficult, I think this is not a good field for very high intelligent people. So 3D sensing is very difficult. So this field is suitable for very intelligent people to join this field. So just like student like you.
So I completely agree because we work in the same field. So that's why I admire like Orbeck has accomplished it within the past 7 years. You actually can make this technology, bring the technology to the consumer level. Yeah, that is very, very difficult to do. So let's move on to the next question. So the one audience asked about what is actually the best 3D reconstruction technology that will be used in the cell phone in the future? Not right now.
I think nothing is best. So in cell phone, they have face-facing camera. They have wall-facing camera, front camera and rear camera. So front-facing camera, they watch the human face. So this one, the working distance is below 1 meter. So below 1 meter, as Apple, they continue to use structural light. Below 1 meter, the accuracy structural light is the best. And also not only the accuracy, the data reliability structural light is best. Just now I talking about Itop because Itop, when your face color change, or you wear a face mask, so you wear some, like for ladies, they change their face color, then Itop depth information will change. Also, Itop face, if know there is a multiple pass problem, the depth information is not so reliable. But for structural light, they even you change your face, the color, you change you have a nose, but the reliability of the data of structural light is very good. So I believe that front camera, facing camera, will use structural light in the future. And for wall facing, now Apple use Itop. Wall facing camera of cell phone, Apple now use Itop. Itop is the reliability is very good. Itop now the resolution is very low, but each point the data is very reliable. But Itop not so reliable, resolution is much higher than Itop. So I think the wall facing, cell phone company will use Itop as well as Itop. Maybe Itop with combined with like stereoscopy algorithm, and maybe Itop with like stereoscopy algorithm. And also some of the cell phone company also will use Itop for face camera, but this maybe the small percent, is not a big percent. So this is, I think, for cell phone.
Yeah. So what you are trying to say is that there is no one solution for all, right? So it depends on application. So the technology, exactly. We need to use the right technology and do the right thing. So
exactly, the right technology for the right thing. Yes.
Yeah. So there is another question a little bit more like in depth. So they asked about for industrial inspection. There is a specular like reflection, and also could have the transparency. So how would the ORBAC solve this very challenging problem in the manufacturing field?
Yes. In manufacturing field, we face the transparency and reflection problem. Actually, reflection problem we can deal with some. Okay, you capture the reflected data, for example, reflected fringe, and if the surface change, the fringe will change. Your projector fringe don't change, your reflected surface change, and then the fringe pattern you capture will change. So this we can measure the surface change of the reflected object. And for transparency is very difficult. Transparency almost no way, because optical you don't see it. You cannot deal with it. But normally no 100% transparency. Normally transparency is like 90% or 95, 98%. But if you have 2% reflected back, you can do the same thing with reflection. For example, for the cornea, human eye, you have a cornea, and the cornea is transparency, but the cornea shape is easy to measure because it can reflect a little bit light back to the camera, then we can do some measurement. And I think also most of for industrial, you need to tackle with this problem. But for consumer, normally we don't need to tackle this problem. Yeah.
Okay. Thank you. So I think because time, right? I want to comments when actually comments from the audience. They said Orbex's talk 太棒了。so with this, I think we can close today's plenary talk. Thank you again, Dr. Huang, for you to share your company, share yourself, right? So as everybody can see from his answer, his question and his question and answer and talk, he's not a typical CEO or CTO. Only knows how to make money. He actually knows how technology work. What is the real technology challenges in the field? So that actually make Orbeck very unique in the field. So he can lead the company to a very, very far because he understands technology, and I hope that Orbeck the value, right, will exponentially increase in the next few years. So we'll see whether so with Dr. Huang in the driving seat, I think that would be possible. So thank you again, everybody. Yeah, go ahead.
Okay, thank you.
Okay, thank you. So we can, I think we will come to the next session for the keynote session. So thank you, Dr. Huang, and everybody, and Dr.
Thank you.
Yeah, thank you.
Bye-bye.
Yeah, bye.
Okay, so our next keynote speaker session will start in about 3 to 4 minutes. So can everybody hear me okay?
Yeah, bye.
Thank you so much. So Professor Marugo, could you quickly test out your speakerphone?
Yeah, can you hear me? Okay.
Yeah, perfect.
Okay, thanks. Should I start sharing my screen or something?
Yeah, go ahead.
Or okay. Okay, let me know if you're. Okay, are you able to see my screen?
Yeah, it's perfect.
Yes. Okay. So we'll wait a minute or so, or?
Yeah, well, just wait another 2 minutes.
Okay.
Okay, I think it's a good time for us to get started. So first of all, for everyone that's in the conference, welcome back to the first keynote session for today. And together with Professor Qichan Zhang and myself, we will be co-chairing the first keynote session for today. And first of all, it is my great pleasure to introduce the first keynote speaker for today's session, Dr. Andrews Marugo. So Dr. Marugo is a full professor at the Technological University of Bolivar. He got his PhD from the Technical University of Catalonia, Barcelona in Spain, and he's the recipient of the Honors Diploma for Young Researchers from the Spanish Optical Society and the SPIE Defense and Commercial Science Rising Researcher Award and the 2019 Fulbright Visiting Scholar Award. And he will be giving a talk entitled 3D Imaging of the Skin as a Medical Diagnosis Tool, which is very interesting. So now let me transfer the podium to Dr. Marugo.
Okay, thank you. Just 1 second. Okay, I had a. Thank you, Dr. Baywin. Well, hello everyone. Good morning or good evening, depending on where you are. It's a pleasure being here with all of you at the first International Forum on 3D Optical Sensing and Applications. And I'm from the Department of Mechanical and Mechatronics Engineering from the Technological University of Bolivar in Colombia. And I'd like to express my gratitude to the organizing committee for inviting me to speak, especially to Professor Song Chang, and to acknowledge everyone that has made this event possible. So my talk is titled 3D Imaging of the Skin as a Medical Diagnostic Tool. And so I'll be giving a brief overview of the system that we designed for 3D imaging and going more in depth with how we developed this tool for diagnostics. So briefly, well, I'm here. We're all scattered in the world right now, but I wanted to let you know where I'm from. I'm from Colombia in South America, and in the north part of South America. And my university is located in the beautiful city of Cartagena, which is actually was founded in 1533. It's a UNESCO World Heritage Site. It's famously known for its colonial architecture. And this is a photo of our main campus. Actually, our university was founded 50 years ago, so we're celebrating 50 years this year. My lab is basically it's called OP Lab. It stands for Optics and Image Processing Laboratory, and so we're a small team here in the Technological University, and this was the team that worked in this project. Actually, it was a multidisciplinary team with physicians, engineers, and physicists. Okay, so what's the deal with measuring skin features? Well, we're all engineers, and so we like to measure everything, but it's not quite that. It's actually more about designing devices that produce more reliable diagnostics within the limitations of our technology, uncertainty, and the variability of people, which is quite a difficult problem in itself. But we know that our technology is not perfect. However, as Dr. Huang said in the earlier presentation, we are always pushing the envelope. We have to push harder, and we have to improve the technology. So I'm going to talk about 3 things. So first of all, I'm going to tell you why is there a need for 3D imaging for skin test diagnostics, and what are some current limitations in the measurements done with these tests. And third, what was the system or the method that we proposed for 3D imaging as a diagnostic tool. So let's get started. So there's a need for 3D imaging in skin-related diagnostics. There are many tests that are carried out in the skin, and the most popular one is called the skin prick test, which is done to diagnose allergies mainly. There are other tools such as like blood tests, or even the challenge with in case, for instance, of food allergy. But the most reliable and the most accurate one and the safest one, which is quite important in healthcare, is the skin prick test. So, but what is actually the skin prick test? So let's say the physician suspects that a patient suffers from a certain allergy. So basically, they put a small drop of the allergen in the skin of the patient. Then they prick the skin with a small needle, and then they wait a couple of minutes to see if there's a reaction. So it's used for diagnosis, for instance, of food allergies, allergic rhinitis, penicillin allergy, and tuberculosis test, among others. It has roughly a sensitivity of 70%, which is not that bad, not that good, but it's actually the best they have. So it's the tool they have to work with, the tool they have. And most times we engineers have to do the same. So the idea is that after a while, if there's a reaction in the skin, the physician comes and measures with a millimeter graded ruler. There is a negative control and a positive control to test if everything is going all right. And there's typically like a threshold depending on the concentration of the allergen. It could be 5 millimeters or 3 millimeters of the wheel to determine if it's positive or negative. But there's also a problem in that these wheels or local inflammations, they're called papules or wheels, they're not regular in size. So they have to do some type of approximation like an ellipse. Or more recently, they've had like this protocol which they measure something they call the longest diameter. As an advantage, well, anyone can do it more or less with some minimal training, and it requires very little technology. However, as a disadvantage, it's prone to intra and inter-observer error, as you might imagine. There's no digital record of the test, and it's quite time-consuming. But moreover, if we see what the physician is doing, he's reducing to a one dimension, something that is essentially a 3D problem. On the left image, I have a brief description of what happens. And if you see, the skin wheel is basically a local inflammation. So one would think, okay, but why not use like the volume or the area? But the problem is that the height of these wheels is in the order of 100 to 300 microns. They're irregular in shape, and it's quite difficult to measure the area or let alone the volume with the naked eye. So let's go a bit more to talk about the current limitations of how these measurements are carried out and some other problems that they're dealing with. So the allergy test or the skin prick test is not the only test that is done with the skin prick test. There's also the tuberculosis test or the penicillin test, which basically measures the same thing. They measure a wheel, but there are also even diseases or pathologies that manifest itself with certain lesions in the skin. So like we believe that 3D imaging can aid in all of these circumstances. So let's take a look a bit more about what a typical wheel looks like. So it's something that in height, it's something in the 50 to 500 microns or so. They can have diameters as little as 3 millimeters or even below, and something between like 20 millimeters or even a little bit higher, depending on how the reaction is. But the problem is that these wheels are scattered in a relatively large area. So we have to measure each one as best as possible within a large area, which is something not as easy to do. So the physicians came up with a way to do it. So basically, they draw around the wheel with a marker, and then they transfer it via adhesive tape to paper. It gets scanned, some image processing to determine diameter or area, and it works quite good. It's actually relatively precise. Repeatability is increased. It does provide a digital record. However, it depends on the physician's ability to draw the contour. It is quite time consuming, and it requires a lot of manual interaction. So the problem here is that although this technique works, it's seldom used because it requires a lot of time. And it's often mostly used only for research purposes, not in the clinical practice. There have been other attempts at trying to solve this problem doing conventional 2D image processing, but it's actually prone to illumination, skin tone, and measurement, and problems with the measurements. It's not so reliable. So there are a lot of challenges in this field, and so measuring each lesion individually is possible, but it's also cumbersome and time-consuming. And the overall assessment for automatic diagnostic is quite limited. There's always a trade-off between field of view and resolution if we want to scan a relatively large area. We also need fast acquisition, and in the skin, if you know a little bit about how the skin works, the skin is not a single layer; it has many layers. So we have subsurface scattering. Skin tones vary significantly. There might be hair presence and others. So we thought that, well, 3D photogrammetry is possible, but it requires a large number of images. It does not give dense 3D data. It also depends a lot on the object texture, and requires significant computation time. So let's look a bit more closely about the system that we developed and how we carried out the automatic measurement. Okay. So let's begin with a typical Fringe projection system composed of a projector and a camera. Let's say our fringes are sinusoidal and follow this typical equation. And we're considering using a Fourier transform for acquiring only a single image to avoid motion artifacts or other problems. So as you know, well, we capture a fringe image of the object, and then we filter in the Fourier spectrum. We get the phase, we calibrate, obtain absolute phase, and then we calibrate to obtain the 3D surface. But given that our wheels have roughly heights in the order of several 100 microns or even lower, and their size, but they're also scattered in a relatively large area, so we have to consider a field of view at least of something of like 200 by 200 millimeters. So we wanted to obtain the best object height sensitivity as possible, which is given by this equation. So given that all parameters are fixed, we can modify all of the parameters, but still the best parameter to modify is the fringe width or a step or the frequency. So assuming we increase the fringe the frequency, so but by how much we have to increase it to be able to measure those wheels quite well. So we assume certain values for given the field of view and the camera and the projectors, and assuming something like 0.5 noise and 1.5, so we get something like a delta phi of 1.5 radian, which gives us a step of about 0.44 millimeters for these fringes. It's really small, but it's still doable. And we also wanted to use off-the-shelf components and something that could be done quite compact and without requiring a lot of hardware. So we ended up using an analog, actually LED pattern projector with a high spatial frequency with uniform. It provides quite a uniform illumination. It even allows for time-flowing imaging, which is quite good because of the surface that we want to scan, and a large projection field of view as well. Obviously, it's not programmable, but still, given that the surface that we are trying to scan is really smooth, so we really have no problem by not using phase shifting. So that's the device that we used in this project. So we had some requirements, something like a field of view of 300 by 300 millimeters. We wanted to obtain the best height sensitivity possible. We wanted to have fast acquisition. We wanted to have the texture image, and we wanted to use off-the-shelf components and nothing customized or so. So this is the setup that we came up with. To increase the field of view, we use 2 cameras, and we use some laser lines to get absolute phase. And this is the analog projector. So we perform a calibration that we came up with to avoid having to register the partial reconstructions of the camera. So we obtain the partial reconstructions are automatically merged within a whole global coordinate system. So we scan through a volume, and we acquire these images, a texture image, a fringe image, and a laser line image by moving a checkerboard along the Z direction. So our calibration, basically, by acquiring all of those images, consists of Z, calibration, XY, and also determining the fringe order to obtain absolute phase. So let's look a bit about how we do each calibration. The depth calibration basically consists in processing the phase or the fringes from the white squares of the board. Having adjusted that phase, we do phase unwrapping, and then we adjust the phase to the depth, to the measured phase, using some polynomial, which works quite well, and we tested it. Also, because it's not a telecentric system, we have to do a fitting for the transversal for XY. So we basically detect the checkerboard corners, and we get X and Y coordinates, which we also fit depending on the depth via polynomial regression. Because we need absolute phase to ensure the accuracy of the calibration, we actually get the laser line, and then we also fit it with a polynomial to get the absolute phase. So this is the system at the lab with the mannequin. So basically, we acquire the images, the laser line, and the 3D reconstruction. Here are the partial 3D reconstructions, and this is the whole field reconstruction, and automatically merged. So this is a validation test that we did on a staircase with 100 microns steps, and as you can see, this is raw data. The accuracy is quite good for measuring steps of 100 microns, which was something that we were aiming at. We also determined the transversal calibration, which was actually quite good for given the field of view, and that these are conventional lenses, not non-telecentric lenses. Okay, so here I'm showing the system as well, now with a patient. As you can see here, this is a capture of camera 1, camera 2. This is the overlapping region, and this is the 3D data that we got. If we want to look at how the whole pipeline goes, so we acquire these images quite rapidly, below 100, something like 100 milliseconds or something like that. We acquired the three images. So we process the phase to do phase unwrapping, and then we get the X, Y, and Z coordinates for the 3D surface, and so we get the 3D reconstruction. So now let's look at a real test of a patient. This is another one, and this is the 3D reconstruction with the texture. Okay, so now we have the 3D data, and we are interested in performing diagnosis. So we want to measure the wheels automatically and robustly. So we came up with this algorithm that I'm showing here with these steps. So as input, we have the 3D surface of the patient's forearm. So we have to, because the wheels are small, imagine that we have like a small house on top of a hill. So we want to remove the hill just to measure the house, the height of the house, or the diameter of the house in this case. So we have to do some global surface removal to get the wheels. We also have to do wheel detection to get each one of them, and then we do some surface centering to be able to measure reliably to put in the center of the patch the wheel, and then some parametric fitting to obtain an estimate of the diameter of the wheel. Okay, so our global surface removal technique consists in Gaussian pyramid decomposition. So we basically decompose our surface as a Gaussian pyramid, and then as a Laplacian pyramid. If we take a look closer here, in the Laplacian pyramid, as you can see, the first levels of the Gaussian pyramid are basically noise, and the lowest level of the Gaussian pyramid is actually the global surface. So if we actually mask out those parts and then collapse the pyramid, we actually reconstruct a signal or a 3D surface, that has been filtered, and also that is flat, that does not have the global surface. And it's actually quite a good technique for filtering scale space dependent signals. Okay, so for the wheel detection, we actually implemented a multi-scale filtering with location of Gaussians, which basically by changing the width of the Laplacians. So we have a 3D stack, and then via non-maxima suppression, we are able to detect the location and the approximate size of each wheel. So we extract patches according to the size of each wheel. Here is for reference the wheels, and this is the input surface in this stage. So okay, so we now have the wheels extracted, and so we want to measure approximately, and this is something that we took a lot of time. So we do PCA to center to get like the main to get basically the centroid of the local centroid of the wheel. But we thought about a lot about how to estimate the diameter in a robust way, because the idea is that this is not regular, as you can see in shape. And so we actually thought of trying to do something mathematically that mimics what the physician does. So we came up with a model that it's based on 2D super Gaussian functions. So if we use these functions on this data, it comes that it's basically trying to find like a bounding box. As you can see here, we have two different wheels. This is a more regular shaped wheel, and this is a kind of like a more irregular shape. As you can see, it has like some tail here. But basically, that's what the physician does. It tries to move the ruler to try to estimate the larger diameter of the wheel. So our box is basically, so our 2D Gaussian function is moving and trying to fit that wheel in a robust way. And if you see here, the reference measurement of the physician was 4.47, and our method obtained 4.95. It's important to note that because it's not a regular object, those measurements can vary, but the reference was obtained actually by having the physician measure the wheel on the computer screen, the 3D with the 3D surface, and it was computed from three independent measurements to get that an estimate of what the reference was. Here's 10.94 and 10.38 obtained with our model. We validated also with spherical caps, as we show here. We also moved the caps in different parts of the field of view, and we have different sizes. And as you can see, the reference measurements are, for instance, 9.08, and we obtain, depending on the camera, something really, really close, 9.04. This is the diameter, okay, not the height, because what the physicians are interested is in the diameter. So we are trying to mimic with our system what the physician does, to have something that's quite, that he can relate to. If we give him, let's say, an estimated volume of the wheel, he might not be able to understand that with the current standards or for diagnosis. So this is actually like our patient zero that we tried our technology on. And we tried, so basically they do a lot of tests, the skin prick test along the arm, but not all tests turn out in wheels. So in this case, he had 1, 2, 3, 4 wheels. This is the overlapping region, so we have duplicate wheels there. And if we look at the measurements, so we wanted to test how repeatable our system was in measuring the same thing, but under different circumstances. So we had the patient move its arm across the field of view, and then we measured again, and he moved his arm at another part, and then we measured again. And if you see here, for instance, one of those wheels, one of the smallest ones, the physician had 4 millimeters. He can only actually measure within plus minus millimeters. And our system was able to measure, let's say, 4.54 in one position, in another position, 4.89, 4.69, 4.88, 81, sorry, and the second camera, 4.59. So if you see, I'm just highlighting one here, the coefficient of variation is quite low. So that's one of the most important parts about trying to have a system performing something that a human being can actually do, but not as accurate and not as repeatable. And actually, our system is able to do that. So this measurement, if we see it there, is basically this shown. This is what the physician measured, and actually his error is in something within plus or minus 1 millimeter. And our coefficient of variation by different positions and measuring the same wheel, it's quite accurate. And the good thing about this is that, or the most impressive thing is that it's part of the skin and it's a local inflammation, and we are able to measure it quite accurately. Whereas with a ruler, you cannot do that. So later we had more patients and something in the order of, it was 9 patients, but overall something like 70 or 80 wheels between all patients, which I am plotting here. So basically, in the top part of the plot, this is called a Bland-Allman plot, in which basically you have here at the bottom the average of the both measurements, which is like your best estimate of what the true value is, and this is the difference between the two measurements. And actually, this is the reference against our automatic measurement. And as you can see, well, ideally it should be close to 0, the differences, but also the dispersion has to be relatively low, ideally for a good measurement system. And if you see the 1.96 standard deviation plus or minus gives something for our system of 0.71 millimeters or minus 1.39 overall. And this is the estimated wheel diameter versus the reference, which is quite good. And this is for the manual measurements with a ruler based of the physician for those same wheels. And as you can see, the dispersion and the Bland-Allman plot is quite high. And obviously here, the scatter plot as well is not as good as our system. So not only we are showing that our system is accurate, but also it's the repeatability of our system is quite good. So, well, basically to conclude my talk, we proposed a 3D imaging system for the acquisition of the skin prick test for use in allergy diagnosis. And this system provides a robust method for the automatic measurement of skin wheels with high accuracy and high repeatability. Okay, well, so that was my talk, and thank you. I also like to thank this work would not have been possible without the collaboration of our students and our other colleagues, and the funding from MinCiencias and our university. And thank you all for your attention. So I'm here open to questions.
Okay, many thanks for Professor Marugo's great speech. So I have a quick question for you. Like, so you can get very highly accurate 3D geometry of the skin using the fringe projection. So will this be used in combination with other biomarkers, or simply the quantification of 3D would be good enough for a diagnosis?
Okay, thanks. That's a really good question. I overlooked at it, and in a certain sense that it's not the only. So let's say that you go to the physician. So he has a clinical history of you. He asks you some questions, and he also relates other data with this measurement. So, but we want to make this measurement as reliable as possible. This test. So that he is, let's say another physician does the test, and he might not believe the test that another physician made, and he tries to repeat it. So because of this intra and inter observer error. So to answer your question, they do use more data for the diagnosis. It's not a single value that gives you, okay, you're positive for this or negative. But we want to make this data as accurate as possible. And we believe that our system, or let's say our method, provides that.
This is great. And there's a technical question from the audience. Say, is there a standard for the density of the pattern you project?
Standard. Is there a standard? In what sense?
Like, what's the period of the fringe pattern you're going to use?
Oh, okay. Yes, yes. Okay. It's the period is something. It's like 0.3 millimeter. The step the fringe width. And yeah, it's at least for that case, it's enough for what we needed.
Okay, perfect. So due to limited amount of time, so this is the only question we can have right now. So apologize for the other audiences. And so just thank again for Dr. Marugo's great speech.
Okay, thank you. And thank you everyone for your questions.
Thank you.
Let me, okay. Just 1 second. Just stop sharing. Okay.
Okay, so right now, it is my great pleasure to introduce our second speaker for today's session, which is Dr. Fan Xu. Wait a second. So Dr. Fan Xu is a postdoctoral researcher at Purdue University, and he got his PhD from the University of Chinese Academy of Science, and where he also got his Best Dissertation Award. His research focuses on 3D super resolution imaging of tissue specimens and single molecule localization analysis for fixed and live cells. And now let's turn the podium to Dr. Xu. So Dr. Xu, you are muted, so please unmute yourself.
Oh, can you listen, hear me?
Yeah, now it's perfect. Thank you.
Okay, should I share my screen?
Yes, go ahead. Please share your screen.
Okay. Can you see my screen?
Yeah, perfect.
Okay. Should I start?
Oh, sorry. Please go ahead and start. Yes.
Okay, thanks. Thanks for introduction. And my name is Fan Xu, and I'm a postdoc associate at Fanghuang's lab from Purdue University. It's my pleasure to present our current work, three-dimensional superillusion imaging in whole cell and tissue specimen. The next scale of the biological research is from atom to cellular structure. The most commonly used methods are the electron microscopy and the net microscopy. However, for net microscopy, due to the diffraction limit of the net, the best resolution we can achieve is around 250 nanometer, which is a similar size as mitochondria. The electron microscopy can achieve nanometer or sub-nanometer resolution. However, it cannot image live cell and has limited field of view. The superillusion microscopy allows us ultra-high resolution imaging target molecule and is compatible with the live cell. Therefore, it provides opportunity to observe the cell structure, dynamic, and interaction at nanometer resolution. Here is the concept of single molecule superillusion imaging. When light emitted by a single molecule goes through the optical system, it will form a pattern. We call it a PSI for short. Due to the diffraction limit, even if the infinite small molecules, the best PSI we can achieve is around 250 nanometer in natural and around 500 nanometer in axial. This is the simulation to show how this in fact. The left part is the adenine structure. Due to the diffraction limit of light, we can only observe the blurred image showing in the right, which is commonly seen in the traditional net microscopy. The concept of the single molecule superillusion microscopy method is used the photoreadable or photoconvertible dyes to isolate its individual molecule at a different time point. Then we can pinpoint their location with very high precision. Sorry. Oh. From this simulation, we can observe over many frames. We can resolve the features periods cannot be seen. Because of this breakthrough, it won the Nobel Prize in 2014. Here is the wide field fluorescent image of the nuclear protein 998 in Cal7 cell taken by our colleague, Dr. Donghan Ma. We can observe the individual puncture of the nuclear pores. When we realize it using the super-resolution microscopy, we can see the much more detailed structures. When we zoom in a specific region, we can clearly see the significant contrast between the diffraction limit image and the super-resolution image. We can not only observe the distribution of the individual pores, but also we can observe the ring next structure around 40 to 60 nanometer. Furthermore, I would like to talk about the 3D super-resolution method. The core of the 3D super-resolution method is infer molecule position inside specimens from its emission pattern. For example, the osmometer-based method uses silicon lens to create two slightly different focal plans around for the X and Y direction. By recognizing the orientation of the molecules, we can know the Z position of molecules. In contrast, the double helix method uses SLM to generate double helix pattern. The biplan uses two plan to detect the appeal of PSF. 4-pi encode actual position into the complex interference pattern. Then we can decode this emission pattern from actual position by using the theoretical model or the model generated from the fiduciary marker. This process, we call it in vitro calibration. For example, the top parts are raw data connected from our microscope with different 3D image modality. For osmometer, we can see the non-overlapping molecule as a different shape. For biplan, we can detect single molecule from two plans. The bottom parts are the theoretical model from these two image modalities. For example, the osmometer elongated in the X direction when below the focal plans, where above the focus, it will elongate in the Y direction. By carrying out in vitro calibration, we can find out which PSF belong to the specific Z position. Until now, we know for the in vitro calibration, we can use the theoretical model or the model generated from the fiduciary markers. However, photons emitted by this fiduciary marker never go through the samples. In contrast, the photons emitted by single molecule inside the specimen are highly affected by the sample aberration, which is unknown. The PSF obtained from this fiduciary marker is no longer accurate. For example, this in which PSF is taken from the fiduciary marker along the axial direction. This PSF blinking data set is taken from the tissue specimen. We can observe the PSF from blinking data sets are distorted along the diagonal direction, which is totally different with the in vitro PSF. This is a simulation to show how inaccurate model will affect the reconstruction results. We simulate the axial distribute double line structure at different image depths. We can observe at the 0 micron depth, the reconstruct structure is almost close to the ground truth. However, when we image deeper, even at 6.7 micron, the reconstruct structure is start to appear as an obvious distortion, especially along the axial direction, and become worse and worse with increased depth. So this inaccurate results raising the questions: can we retrieve an accurate PSF which can reflect the sample-induced aberration. When we're looking at this typical movie, we can see many PSF shown in the green boxes. If we isolate these subregions, we can consider this emission pattern as random samples from the underlying PSF we want to retrieve. However, due to the randomness, the relationship between this detected emission pattern and its corresponding in situ PSF is unknown. So what we really seek is to reconstruct the in situ PSF, which are showing on the right, if only we can assign each emission pattern to its correct positions. To do this, we propose an in situ PSF retrieval method based on the blinking dataset in the whole cell and tissue specimen. We call it INSPIRE. INSPIRE starts with detecting the emission pattern of the single molecule from the blinking dataset. And this emission pattern can be treated as random samples inside the specimen, and it will form a PSF library. Then we use a pupil function. It can represent the waveform distortion at the pupil plane of microscopy, which include both magnitude and phase of the electric field. By using this pupil function, we can describe the 3D PSF at different axial positions. For example, if we have prior knowledge of our image system, we can, for a pupil with a mechanism in this case, we can generate an initial set of reference PSF and different axial position. Then we can calculate similarity between the PSF library and this reference PSF and assign each molecule in the PSF library to a center group. We can observe the PSF are similar in each group to each other, are dissimilar with the PSF in the other groups. Then we can align and average PSF in each group and carry out phase retrieval to form an updated pupil function. Based on this updated pupil function, we can generate a new set of reference PSF and start a new round of assignment process. And we continue, iterationally continue to this process many rounds. The reference PSF will be antithetical to the PSF library, and we have reached at the final 3D PSF model. We can say the INSPIRE will construct an in situ 3D response directly from the single molecule dataset. Therefore, we can use this accurate model to reconstruct the superannuation volume through the average specimens. And to build a unique model, the 3D image modalities must avoid degeneracy. The degeneracies appear when more than one waveform distortion have the same emission pattern. For example, this positive and negative asymmetric aberration will generate the same emission pattern as the opposite axial position. However, we can break up this degeneracy by using the prior knowledge of the asymmetric orientation, or we can use a biplane configuration, where a pair of PSF can be detected at different planes. To mimic the condition we image 6 specimens, we test INSPIRE in the blinking dataset obtained on the time 20 protein in the Cal7 cell. First, we insert the deformer mirror into the pupil plane of microscope and introduce a controllable distortion. The DIM can introduce different amount of aberration. Here, we select from the asymmetric aberration to the tertiary spherical aberration. This is the simple effects the diagram. The detail can be seen in our paper. Next, the distorted emission pattern can be detected on the camera. Finally, we can use the INSPIRE to retrieve the in situ pupil and its corresponding aberrations. This is the experimental result. By changing the input aberration from DM, INSPIRE can retrieve the corresponding aberrations we're showing on this matrix. We can observe from this matrix is quite diagonal from the mode 5 to mode 22, and its accuracy decreases when we estimate the next with modes. This indicates the capability of Inspire to retrieve the in situ PSF directly from the in situ from the single molecule dataset. Then we go back to the previous discussion. This in vitro PSF is taken from the Fiduciary marker along the axial direction. This Inspire retrieved PSF is coming from the blinking dataset. We can observe the Inspire capture the emission distortion which is showing on the blinking dataset, which is highlighted on the green boxes and the yellow boxes. Then we compare the simulation results at different image depths. In compare to the in vitro calibration, the reconstruct structure by Inspire maintained high fidelity up to the 27 micron, and at the 45 micron, the reconstruct structure by Inspire start to appear tilted. However, it's still less distortion than the in vitro calibrations. Using the Inspire, we can build the accurate model directly from the single molecule datasets. Therefore, we can improve both accuracy and precision in our reconstruction results. Here you can see the reconstruct the TOM20 protein in COP7 cells, where the cross-section shows the memory control of the mitochondria. In compare to the in vitro reconstruction, Inspire improves in terms of sharpness and as well as reduce artifacts. Here is the Inspire retrieved PSF and its corresponding pupil. In compare to the in vitro one, the Inspire capture the increased severe aberration since we image 9 to 11 micron deep. Here is the 3D super-resolution reconstruction for pair with the mitochondria dataset. We immune fluorescent label TOM20 with NX 647. The total number of localization is 1.1 million, and the average XY precision is 8 nanometer, and Z precision is 21 nanometer. Here is the X-ray cross-section. Here is the YZ cross-section. Here is the XY cross-section. Being able to retrieve the accurate PSF, we then can image the more complex case tissue specimens. Here is a 3D super-resolution reconstruction for amyloid beta plaque from a mouse model of Alzheimer's disease. We image 30 micron brain tissues. The total number of the localization is around 500,000. The XY precision is 7 nanometer, and the Z precision is 28 nanometer. Here is the X-ray cross-section. Here is the YZ cross-section. Here is the XY cross section. Oh, sorry. We also have many other demonstrations, include mitochondria, lambda antennate in Cal7 cell, amyloid beta plaques, and dendritics in the brain tissues, and the elastic fiber in the mouse catenage. I would like to stop these movies. If you are interested about it, you can look at our paper. So finally, for the summary, the sample-induced aberrations distort the PSF in an operable manner. Inspire can retrieve in situ PSF directly from the single molecule blinking dataset. Therefore, we can reconstruct the superillusion volume through the aberrate specimens. Inspire extends the application of the superillusion microscopy from the selected cellular targets near cover slip to the intra and actual cellular targets deep inside the tissues. At last, I would like to thank my supervisor, Professor Fang Huang, and my collaborator and the co-author Donghan Ma. And I would also thank our collaborators, Dr. Sarah Carey from the Purdue University, the Dr. Gary Nelson from the IU School of Medicine, and Dr. Peng Ying from the Harvard University. Their team worked closely with us on this project. And also thanks the funding source, NIH and DARPA. Thank you very much for your attention.
All right, so I think we got a couple of minutes for questions. So I actually have a question. So, I've seen that there are some noises in the very high resolution images you got, and so would that be impacting the extraction of the point spread function?
You mean this structure, dot-net structure?
Yeah, it says. Yeah.
Oh, actually, it's not noise. Actually, it's
okay.
It's the specific bonding to our structure. It's also the molecule structure. So it's unspecific dyes inside the cover slip. So it's not a noise.
Okay, I see. Apologize for my ignorance on that part. Okay. And I got a question from the audience. Say, you got really high resolution for the 3D imaging for the cells. So what would be the major application in that sense?
Oh, at the beginning, we talk about the superillusion method is have the own advantage because they can achieve nanometer resolution and is compatible with nerve cell. But the previous discussion is more focused, the study is more focused on the inside cell around the cover slips. However, because when we image tissue or whole cells, it have sample-induced aberrations. This cannot to reduce. So at this point, because our method is directly to retrieve the in situ PSF from the blinking dataset, it can build the accurate model. So therefore, we can to explain the application from the selected cellular targets near the cover slip to the more complex case, for example, the tissue imaging. So for the tissue image, it's the more realnetics because for our human study, this is inside the tissue. It's not an individual molecule or the cell. So this is where it extends the more application for the superillusion microscopy.
All right, that's very impressive. So another question I have is, what is right now the most extreme accuracy you can achieve for your method?
You mean the accuracy is the localization precision?
Oh, sorry, not the accuracy. Right. I'm talking about the resolution. Yeah.
Oh, resolution. The normal in our method, the resolution is in the XY precision, XY direction is around 20 nanometer, 10 to 20 nanometer. But in the Z resolution is around 50 nanometer. This is our method.
Okay, I see. So is there any questions from anyone that's in the conference room? So if you have a question, please feel free to unmute yourself and speak.
Okay, thank you.
Okay, so yeah, and let's thank Dr. Xu for his great sharing about his work. And so now, so Professor Qichan Zhang, please feel free to take over the chairing for the session.
Okay, I'm here. I will be checking. Thank you.
Oh.
Okay, can you hear me?
Yes, perfect.
Okay. Hello, everybody. According to our schedule, next section will be begin at 14 minutes later. Am I right? Okay, let's start at 11:15. Okay, see you later.
Yeah, we have a coffee break, so we will start at yeah, in about 13 or 12 or 30 minutes. Yes.
Okay, Dr.
Hello.
Huang, please
Yeah.
double check.
Professor Zhang. Nice to meet you. Yeah. Could you hear me again?
Just test you. Yeah,
Clearly?
yeah. Perfect.
Okay.
Perfect. Okay. Just test your device.
So maybe I can share the screen now.
Yeah.
Okay.
Yes. Yes.
Could you see that? Yeah. Okay.
Yeah. I can see your screen. And what's the exact time on your New York City
The same, but just at night.
at night? Okay.
Yes.
Okay. Hello, everybody. It's my great honor to judge this session. And in this session, we have two speakers, invited speakers, Dr. Huang and Dr. Li. And firstly, please give me seconds for introduce myself. I am Qichan Zhang from Sichuan University, China, and I'm doing some research work on optical metrology, especially on 3D shape measurement for dynamic objects, dynamic process, which shape is changing and something else. And now let's introduce the first speaker, Dr. Li Huang. Dr. Li Huang got his PhD degree in optical metrology from Nanyang Technical University in Singapore in 2013. After that, he joins NSLS Optical Metrology Group as a postdoc at Brookhaven National Laboratory in USA. He started his career as an assistant physicist at NSLS since the year of 2015. And now he's working as a physicist in the metrology group. His research mainly focuses on developing techniques and instruments for ex situ and in situ synchrotron mirror metrology, such as stitching, interferometry, deflectometry, and wavefront sensor. He was develops the real-time algorithm for deterministic Gaussian. And today, his topic is ultra precision optical surface metrology for synchrotron mirrors. Okay, let's welcome Dr. Lei Huang. And it's your time, please.
Okay. Thank you for introduction, Professor Zhang. And thanks for having me. It's absolutely my pleasure to give this online talk at our iFOSA
I sincerely appreciate Professor Zhang Song, Professor Xu Jing, and Professor Zhuo Chao, and Professor Feng Shijie, and of course other organizers, as well as very important volunteers for their efforts to provide this wonderful platform to share our knowledges between all of us. I hope everyone enjoying this forum. I'm Lei Huang, working at the National Synchrotron Light Source 2 at Brookhaven National Laboratory. Usually we call it BNL for short. BNL is one of the national labs in the United States, located at the Long Island, not far away from New York City, with roughly 2 hours driving distance. At NSS2, I work as a metrology scientist for characterizing synchrotron optics, mainly the X-ray mirrors, and sometimes for the in-situ X-ray wavefront sensing as well. Today, I would like to talk about the ultra-precision optical surface metrology for synchrotron mirrors. I guess most of the audience are not very familiar with synchrotron mirrors, so I will first introduce these special mirrors used at synchrotron radiation facilities, followed by describing the metrology instruments we have here at NSS2. I will show several cases to demonstrate how we use these metrology tools to inspect mirrors for the NSS2 beamlines. In addition, in our group, we have deterministic optical fabrication capability, and I will show how we can use our ultra-precision metrology data to feedback to the fabrication process. At last, I would like to discuss what we are currently doing and what is expected in the short future. At a synchrotron radiation facility like NSS2, electrons are accelerated close to the speed of light and then injected into the storage ring. The X-ray beam is generated starting from the bending magnets or insertion devices, such as undulator or wigglers. The X-ray beam will pass the X-ray mirrors, slits, monochromator, and some kind of focusing optics, for example, the KB mirrors shown here, or it can be zone plates, compound refractive lenses, or multi-layer lower lenses. And finally, the beam will focus into a spot at end station for the user experiment. Used at a small grazing incidence angle. The synchrotron mirror is one of the key optical components to deliver and focus the X-ray beam. Usually, the synchrotron mirrors are made of silicon or fused silica, typically 100 millimeter to 1 meter long, sometimes can be even longer, with coatings. The coating material can be gold, platinum, palladium, or rhodium. The mirror surface can be totally flat, or it can be in the shape of circular cylinder, elliptical cylinder, toroidal, or ellipsoidal shape to make the focus. Depending on the beamline design, this mirror shape can be fixed, or it can be deformable with mirror benders at the two sides. By many BIMOF actuators. Here is a picture of a BIMOF mirror. Nowadays, the specification of the synchrotron mirrors become very tight. Here, I just share some typical numbers to give you a taste. For the partially coherent beam, the mirrors are usually specified on slope arrows. A typical number is around 100 nanoradian to 200 nanoradian RMS. Here, the RMS is short for root mean square. For the fully coherent beam, the mirrors are usually specified on height arrows, usually around 1 nanometer RMS. The surface roughness should be less than 0.3 nanometer RMS. By looking at all these characteristics, not only due to the tight specification, but also its long dimensions in one direction and different surface shapes with different parameters, the synchrotron mirror can be treated as extreme optics. Before installing these extreme optics into the beamline, each piece of these mirrors should be inspected to be sure it meets the specification. And the actual effective area on the mirror surface is a narrow rectangular region. In the beam direction, or we usually call it tangential direction, the surface can be a sphere in 1D, so it's a part of a circle, or it can be in an ellipse with a height PV, peak to valley, varying from a few microns to a few hundreds of microns or even more. And in sagittal direction, it can be totally flat. Of course, the surface can be curved in 2 dimensions as well, as this toroidal shape or a small section of ellipsoidal shape. Here I take the fully coherent X-ray beam as example to illustrate why such a high requirement on the surface height is needed, based on the Mauricio criteria. In order to preserve the X-ray wavefront with the diffraction limit, the wavefront error needs to be less than lambda over 14 in RMS. Here, the wavelength lambda is about 0.1 nanometer for hard X-ray and 1 nanometer for soft X-ray. So lambda over 14 is actually a very tiny number in picometer or tens of picometer level. But thanks to the small grazing incidence angle theta, which is at the bottom of this equation, the mirror surface height is kind of relaxed a little bit, but still at 1 nanometer RMS level. It's very challenging to the metrology, because to inspect this 1 nanometer RMS on the mirror surface height, our metrology needs to be around 0.3 nanometer RMS or even 0.1 nanometer RMS, ideally. At this level, not only the metrology technique itself, but the mirroring environment also become very critical, such as temperature stability and the vibration and the air turbulence. For sure, it's never easy to measure sub-nanometers with the desired mirroring range and mirroring area. Generally, there are two important techniques currently used in the synchrotron mirror metrology. The first one is deflectometry, which essentially measures the surface slope based on the law of reflection. When the local surface changes in an angle alpha, the reflected beam will change 2 alpha in angle. By using an angular detector, the local slope can be profiled with a scanning or stitching mechanism. The other technique to measure synchrotron mirrors is a well-known interferometry. In principle, we can have two coherent wavefronts. One is reflected from the reference surface, and another one is reflected from the mirror under test. They will interference with each other and generate the interferograms. The surface under test can be measured out by analyzing the captured fringe patterns. Let's look at the deflectometry method first. The point-wise scanning deflectometry uses a point angular sensor as a detector. It mainly includes the long trace profiler LTP, which is very famous in this field, and nanometer optical component mirror machine (NOM), and nano accuracy surface profiler (NSP). The LTP instrument is developed by Dr. Peter Dagat and Dr. Shinan Qian in late 1980s, right here at BNL. With several upgraded versions in the last decades, it evolves into an LTP optical head with a moving hollow printer prism. The hollow printer prism will always make sure the output beam be perpendicular to the input beam, even with some pitch angle errors due to the carriage movement in the scan. In 2004, the NOM was proposed at BC2 light source in Germany. By replacing the LTP optical head with a commercially available high-precision autocollimator, which enhances the measurement repeatability. However, there is a limitation of using the scanning pentaprism. The length of the optical path will keep changing when the carriage is moving during the scanning. We can imagine when the carriage is moving closer to the autocollimator, the beam path will become shorter. However, the calibration of the autocollimator is usually carried out with a fixed walking distance, and the walking distance will play an important role to the systematic error once the pinhole is used here. In this case, there is a condition mismatch between the calibration and the actual measurement. To overcome this problem, Dr. Shinan Qian in our group developed the Nano Accuracy Surface Profiler, NSP, by using an additional sample beam AC. AC stands for autocollimator, with a fixed walking distance to the surface under test. The reference beam AC is only used to track the pitch angle of the motion, which is typically limited within a very tiny angle range, about 10 microradians. This NSP setup is now the best instrument in our group in terms of slope measuring range versus slope measuring repeatability. Here, I would like to show an example of the mirror inspection by using the NSP. These two mirrors are the horizontal and vertical nanofocusing KB mirrors for the SRX beamline at NSS2. They are in elliptical cylindrical shape with different ellipse parameters. The middle figures are the measured slope profile. After removing the target ellipse, the slope arrow of each single scans and their averages of 100 scans are shown on the right plots. The result shows these two mirrors are under specification. After confirming by us that this set of KB mirrors meet the specification, they can be installed at the beamline for commissioning. Apart from the point-wise scanning deflectometry, we have stitching Shak-Hartmann system developed by our group leader, Dr. Murad Idia, in a close collaboration with a French company. It uses a Shak-Hartmann wavefront sensor as a slope detector. It can give 2D slope arrays in a single shot. By redundantly acquiring the slope data with large overlaps, the X and Y slopes of the whole surface can be stitched out. The 2D height map can be reconstructed by using an integration process. We have been using this stitching Shak-Hartmann instrument to inspect the X-ray deformable mirror. Here is an example. To inspect this bimorph deformable mirror, at first, we need to control this deformable mirror to its target shape as close as possible. We propose a fast method to drive the mirrors by looking at its local curvature from the measured slopes. We first measure the surface slope and calculate the slope arrow, and then calculate the local curvature arrow where the actuators are located. By correcting the local curvature arrow in just 2 iterations, we successfully drive the bimorph mirror from initially more than 900 nanoradian RMS down to less than 200 nanoradian RMS, which is under the specification of this mirror. Then this bimorph mirror is ready to be installed at the beamline with our suggested voltages as a reference for the beamline scientist. The other important technique for X-ray mirror metrology is interferometry, which measures the surface height directly. Since the synchrotron mirror has a relatively longer dimension in one direction, if the mirror surface is close to flat, it's a good option to use this grazing incidence configuration because it can cover the whole mirror surface in a single field of view. In our current project of the metrology for the cryo cooling mirror, we are going to use this technique to measure the deformation on the cryo mirror surface. Instead of using the grazing incidence, we can use the normal incidence as well. Due to the limited field of view of the interferometer, stitching process is necessary in this case. The stitching procedure will aim to accurately connect all the overlapped subapertures with their geometric relations. On this path in this field, Japan is ahead of the rest of the world. Professor M. Uchi's group in Osaka University has developed 2 stitching techniques named MSI and ROTC more than 15 years ago and achieved great success. ESRF, the European Synchrotron Radiation Facility, developed their stitching interferometry system in 2016. HAPS, high energy photon source in China, proposed a scanning interferometer in 2016 as well. SLAC in US also established their stitching system in 2017. Since the same year, we at NSS2 have started to develop stitching instruments from 1D versions and then to the 2D stitching prototypes in 2019. In the same year, Diamond Light Source in UK reported that they started to work on stitching systems as well. The stitching interferometry has been more and more investigated for the applications of synchrotron mirror metrology. If we put the major introduced instruments in the same timeline and classify them into deflectometry, which measures slope, and interferometry, which measures height, we will have a big picture of the instruments developed for the X-ray mirror metrology. Of course, there are many unmentioned research work and development due to the limited time here. Now, I'm going to talk more on our development on the stitching interferometry for synchrotron mirror metrology from 1D to 2D versions. As a learning process, we started our research on stitching by solving the 1D stitching problem which is supposed to be easier to start with. With the help from a visiting scholar, Dr. Junpeng Xue from Sichuan University, we succeed to use triple beam interferometer to track both distance and pitch angle of a translation stage during the stitching data acquisition with a white light interferometer. Repeatable stitching result can be obtained by using this approach. Comparing to the classical stitching, the proposed angular measurement-based stitching method gives much closer result to the physical interferometer data. Later, by adding an enclosure around the instruments and replacing the triple beam interferometer with a high precision autocollimator, the new system gives even better repeatability around 0.3 nanometer RMS. Our angular measurement-based stitching interferometer data measured the mirror from A to B and B to A shows good agreement with the result from NSS2 NSP and the data from Osaka University. This is our first time to get this kind of nanometer level agreement in measuring elliptical mirror using stitching interferometry. This gives us much more confidence to push the stitching in 2D. I believe everyone in this forum can easily get the point that it is always very nice to have a 3D shape of what we are interested in. Here is the same. The 2D height map will be much more informative and extremely useful for the mirror inspection and fabrication. That's why we decided to develop the 2D stitching interferometry platform. The picture on the left is a conceptual configuration with multiple stages for motion control and interferometer for angular and height measurement. The images on the right are the actual prototype with all the stages and their controllers. We developed an NSS2 stitching interferometer software to control all the stages and the Zygo interferometer through the Metropole remote control protocol. We use this prototype system to study the principle of 2D stitching and RASI for ultra-precision metrology. Of course, in order to get decent measurement results at sub-nanometer level, we need to overcome many other practical issues, including the vibration and air turbulence. Here is our measurement result of a flat mirror fabricated by JTAC Corporation in Japan. The clear aperture is about 245 millimeter long and 26 millimeter wide. This is our stitching result. Please note here, the color bar is only within plus or minus 2 nanometers only. And we measured it 30 times. As we can easily see, these 30 times of repeating stitching result shows excellent measurement repeatability at 0.1 nanometer RMS level. After checking the measurement is repeatable, we compare them with the results from other instruments. The same mirror has been measured by the stitching interferometer system at ESRF, the European Synchrotron Radiation Facility at Grenoble in France. The results clearly show very good agreement between these two instruments at different locations on our planet. In addition, we changed the size of sub-aperture of the data acquisition, and we changed the orientation of the mirror, measured from A to B, and rotate the mirror 180 degrees, measured from B to A. All the results are pretty much consistent. We can also convert the 2D measured 2D height map into 1D slope profile and compare them with the slope measuring result from our NSS2 NSP. Again, with different mirror orientations, A to B and B to A, different sizes of stitching windows, and the difference between the slope profiles are well below 50 nanoradian RMS, which is an excellent agreement between all our measurements inside our group. Another example I would like to share here is a measurement comparison of a curved mirror in the shape of hyperbolic cylinder. We measured it in different orientations with our physical interferometer by using sub-aperture stitching and RASI method. In addition, we also use micro-stitching method with our white light interferometer. We compare all these results with the result from Osaka University and the data from JTAC Corporation. From this around about 5 micron peak to valley height map, it's very difficult to see their difference. Once we remove the target shape we can find the mirror height errors measured by different methods are very close to each other. Microstitching with microscope-based white light interferometer will give us better spatial resolution for the high frequency features. We will look into this in the future. In consequence, until now at NSS2, we have several 2.5D, I call it 2.5D, metrology solutions to measure near-flat synchrotron mirrors. In addition to the inspection, another very interesting application of our ultra-precision metrology is to feed back to the deterministic optical fabrication process. We are very lucky to have Dr. Tianyi Wang in our group, developing this ion beam figuring system, IBF system, for the polishing of synchrotron mirrors. We measured the initial shape of the mirror surface by using our stitching platform, and then evaluated the figure error map from the target shape. From the figure error map, we proposed some new dwell-time algorithms to calculate the dwell-time map for the motion of the ion gun with respect to the mirror surface inside this vacuum chamber. After a round of IBF process, the mirror will be remeasured by the stitching interferometer to check where we are and if it's necessary for the next round. Here we will see one of the typical results of the NSS2 IBF by using the feedback from our stitching platform. The goal is to make 100 millimeter by 10 millimeter clear aperture on this mirror surface as flat as possible. The initial figure error is 3.7 nanometer RMS with a concave shape. After first round of IBF, the figure error is reduced to 0.7 nanometer RMS with slightly convex shape. But the dwell time calculation and the shape error prediction suggest us to have another trial, and so we do. After the second round, it ends up with the figure error continue dropping down to 0.5 nanometer RMS with no obvious low frequency trend. This example demonstrates a very nice convergence between our metrology and fabrication process. We are now the only group in the US national labs that has the capability of both 2D metrology and 2D polishing for synchrotron mirrors. In the short future, we will be working on the following tasks related to the metrology. The first project is to improve our existing metrology prototypes into the final instrument for with more engineering thoughts and ideas injected into the design. At this time, through this project, we are targeting strongly curved X-ray mirrors. The second work will combine the metrology result from different instruments to get both accurate form and better spatial resolution. The third future work is actually an ongoing project from US Department of Energy. We're going to measure the surface deformation of the cryo-cooling mirror that is placed inside a vacuum chamber. As I mentioned earlier, the grazing incidence interferometry will be used in this project. All this feature work will bring us new metrology challenges, and we are going to see how they will evolve and what we will learn from them. Finally, I would like to thank many people who helped me in my research. Some of the work presented here in the slides are actually credited to them. The first group of people are my colleagues in NSS2 Optics and Metrology Group. Our group leader, Murat, and my colleagues Tianyi, Shinan, Dennis, Matt, and Kashmira. I got lots of help from them in solving practical problems. Our visiting scholar, Dr. Junpeng Xue from Sichuan University and Dr. Bo Gao from Shanghai Synchrotron Radiation Facility contributed a lot in developing our metrology instruments. I would like to thank them. I also benefited in the discussions and communications with other experts and colleagues all over the world. Some of them directly teach me in technical details. I'm very grateful for it. Once again, I would like to appreciate organizers of this wonderful online forum, iFOSA. At last, thank all of you very much for your attention. I would like to answer any questions you may have.
Okay, thank you, Dr. Huang. And thank you for your wonderful presentation with so many actual precision measurement results. And the first question is from the audience. Some researchers pay attention to the calibration. Ask his or her that the actual precision, nano or sub-nano meter errors distribution in motion. On this scale, how to calibration and evaluate the results? Okay, this is a first question.
Okay.
Please give us some more detail. Okay.
Okay. Actually, I should say this is a very good question. At nanometer or sub-nanometer, there is, to the best of my knowledge, there is no real actual standard. And what we can do is to use different principle of measurement, different systems, different instruments to measure the same surface and compare each other. And this instrument can be at the same lab, or it can be at different institutions all over the world. And we call this round robin. And we need to measure this with different instruments and see. And we think the true value is close to where everybody are around there. If someone is very far away from the others, then we will think very likely the true value is not there. It's probably close to everybody because all the systematic error will be probably different for different instruments. So it's a very tough question to really answer. So I think that's all what I can really reply to this question. It's very difficult.
Okay, thank you. As for me, there's a small question. How about the coating film? Does it some effect bring into the measurement result or not?
Okay, I do see some publications says that the coating actually will affect the mirror surface shape, and also some publications also shows that before and after the coating, the surface figure error are almost the same. So it's highly depends on the actual case. But in fact, yes, the coating will give some impact to the mirror surface. So usually, if we want to really repolishing the mirror, we need to remove the coating and do the polishing, and then after that we need to measure it, of course, and then after the coating we need to remeasure it again to make sure that after the coating the mirror is still under the specification.
Okay, thank you. Thank you. Due to the time limitation, let's thanks Dr. Huang again. Thank you, Doctor.
Okay, thank you. Thank you so much.
Yeah, let's move to the next speaker. Next speaker is Dr. Li Feiwen from Department of ME, Iowa State University. Dr. Li is an assistant professor of ME and the director of Analytical of 3D Optical Sensor Laboratory at Iowa State University. He received his PhD degree in Purdue University in 2013. His research focuses on superfast kilohertz 3D optical sensor, precision 3D optical metrology, 3D point cloud data analysis, and in situ modeling for additive manufacturing. Several of his research works have been highlighted on the cover page of journals, including Optic Express, Applied Optics, and Geotechnic Letters. He is also the recipient of 2020 SPIE Defense and Commercial Sensor Rising Research Award. And today, his topic is 3D optic sensing with temporal multiplexing for in-situ applications. And Dr. Lee, it's your time. That's welcome.
Okay, thank you, Professor Zhang. So can you all see my screen?
Yes, please.
Okay, first of all, many thanks to Professor Zhang's great introduction, and for everyone that's in the conference, thanks for coming to my talk today. And today I will mostly share about what my research group and I have done after joining Iowa State. And by the way, my name is Beiwen Li, and I'm an assistant professor at Iowa State University. And the topic I'm going to share today is 3D optical sensing with temporal multiplexing for in situ applications. Okay, so first of all, because lots of my research is about high-speed 3D sensing, so first of all, I want to talk about why do we want to do high-speed 3D sensing. So we as engineers, a lot of times we try to get some insights from the nature. So for examples, if you're an engineer who wants to design a robotic bird, so you could first of all observe what a real bird flies in the real world. So 3D optical sensing can actually provide a bridge that actually link the nature with the engineering. So basically the scientist can record and digitize what has happened and then do some detailed analysis afterwards to eventually get the insights he or she wants. And speaking about high-speed 3D optical sensing, so one of the most effective approach is the fringe projection. So this should be pretty familiar with a lot of you. So basically, we project the sinusoidal patterns onto the object, and the patterns are going to distort it by the object surface, and the camera is going to capture the distorted fringe patterns to get 3D through fringe analysis. So in fringe projection, one of the most popular approach is the phase shifting technique. So basically here you can see we applied several patterns that applied some rigid shift on top of it. And through the analysis, we can get very high quality 3D. So if we want to achieve high-speed 3D sensing, so basically we need a technology that can switch the patterns that's fast enough. So many thanks to the digital light processing technology, which can actually switch the 1-bit patterns at over 9 kilohertz. And also thanks what Professor Song Zhang did previously about the work which generated the sinusoidal patterns through the defocusing of 1-bit binary patterns. So that in this case, we can actually project 1-bit binary patterns for 3D sensing, and we can reach multi-kilohertz for 3D sensing. And based on that idea, I have previously done some research work, so I can share with you. So what is the current capabilities for 3D optical sensing? So basically, you can see here for some dynamic cases like a flapping flight process or a droplet deposition process, you can get a very high accuracy detailed 3D geometry for the entire process. So you can see here, so basically fringe projection can get a very high accuracy and high speed 3D sensing with massive amount of details. And seems like up to this point, everything is perfect. But however, even though with the current capability, it is not always going to work out as you expected. So here I'm showing you an example where we could encounter some problems. So here, what you can observe here is that we are actually measuring a aluminum plate bending process. So where you could see there are some shiny spots. So if there are shiny spots, you could also see there are corresponding measurement errors on the 3D geometry. And also what you can observe on the surface is that there are some vertical stripes on top of it. So supposedly those harmonic errors should not be there if we are measuring a smooth surface like this. Okay, so these are the problems. So actually there are lots of technology to deal with the shiny surface measurement, and there are also technology to measure the dynamic surfaces. However, so combining to solve the two problems simultaneously would be really challenging in this scenario. So motivated by these problems, so we are trying to do some work so that we can address this. And what we do is that we first of all did a revisit for the DLP technology. So basically, the DLP technology is based on an array of digital micromirrors that can do some fast twists and turns to sense the light and get the different grayscale intensities. And actually, the different grayscales are obtained by doing the time integration. So for example, if you want to get a grayscale of 255, it has to be switched on all the time. And the percentage of the on time will also decrease if your grayscale value is going to decrease. Okay, and typically we will have to capture the entire projection cycle to get a correct decode of the grayscale value. However, right now, because we're using binary patterns, so the binary patterns only have 0 and 255, so we do not have such restrictions. And that is going to give us a lot of flexibilities for the high-speed measurements. And the second thing we observe for the DLP is that in between the projection of two patterns, we typically have to set a dark period in between. So the reason why is that if we don't do that, the mirror won't have enough time to respond to the switching. So, and that is going to cause some overlapping or coupling of fringe patterns in your camera image. As you see here in this image here, we're actually projecting two patterns. One is a high frequency one is a low frequency one. But in the camera image, it becomes coupled into one. Okay, so these are the observations we had right here. So based on these observations, we actually came up with an idea to deal with the measurement of shiny surfaces. So the idea here is actually pretty simple. So for the projection of one pattern, and basically here you can see we have the bright period and also have the dark period. And our idea is that within this one cycle, we're going to project we're going to capture two images. So the first image we call this cap 1 is entirely placed within the projector's illumination cycle. And the second capture is partially within the bright cycle and partially within the dark period. So intuitively with this setup, the cap 1 image should have a much brighter overall brightness compared to the cap 2. So, and this is true, actually, you can see this phenomenon from our captured camera images. And we can actually merge those two with the intensity contrast to fuse to make a HDR camera image. So just like what you did using your camera's HDR mode. And because we're using the camera images in the temporal domain, so we would call this a temporal multiplexing approach. So this idea is pretty simple, but it's amazingly practical to use. So these are some of the testing we did by measuring a rotating fan with 10 rounds per minute. So here you can see that for the HDR 3D result, we can well recover the 3D geometry for this rotating fan. And it can address the problem of the saturation for the bright cap 1 image. And it can also improve the overall quality compared to the noisy the dark cap 2 3D result. So, and we can utilize this method with a camera image acquisition rate of 1 kilohertz. And we're also proud to say that we got this paper recognized as the Best Student Paper Award in the 2019 SPI Photonics Conference. And this award is won by my PhD student, Mr. Vignesh Suresh. Okay, so up to now, it seems like we can well address the measurement of shiny surfaces. But it's actually still has a lot of room for improvements. So here you can see that there are only 2 overall intensity levels, which is not actually very robust for achieving the HDR. So there could be cases where both the cap 1 and cap 2 images are going to saturate. So if this is the case, what should we do? So we actually thought about some way to overcome this. And the way we do is by just utilizing the spectral responses of a color camera to a single colored light. So the idea here is that we would project the patterns using single colored light. And here I'm showing you the green light without the loss of generality. And we're using the color camera to capture that. So after we got the color camera image, we can actually separate it into the red, green, and blue channels. So in this way, we can get 3 different intensity images simultaneously. So actually with this, we can utilize this idea in combination with the temporal multiplexing approach that I just shared. So the idea is like this. So we're gonna do the single color pattern projection. And after that, we're gonna still do the temporal multiplexing approach to get the cap1 and cap2 images. And they're having the different intensities. So the cap1 is brighter than the capture2. So then we're going to separate the capture 1 and capture 2 into their red, green, and blue channels. So after that, we can get overall 6 intensity level images. And that is going to give us a more robust HDR image fusion and resultantly get a high quality 3D imaging. So with that, we actually tested out by testing the tested out using the human facial expressions. So here we actually did a 3D reconstruction for the face of my PhD student, Mr. Yi Zheng, who is also the leading author for the paper. So here we actually selected 3 of the intensity images out of the 6 overall levels. And you can see that among those, basically the HDR 3D result is actually the best. So it avoids the saturation on the faces for the brightest fringe. And it also has the overall higher quality compared to the darkest and also the mid-level 3D results. So basically using this method, we got more intensity levels and get a more robust 3D shape and measurement with HDR. Okay, so apart from doing some research on the measurements of shiny surfaces, we also did some research on addressing the errors induced by the dynamic motions. So here I'm showing you a video of a fast-moving spherical object where you can see on the surface, you see those harmonic errors. So these errors are actually caused by the motions. So if you have too high of motion where your camera cannot keep up the pace with, basically it will cause some additional shifts on the faces of the projectors. So that phase can be denoted by an additional term called a delta right here. In the phase shifting. So knowing this knowledge, we thought about some ways to actually slightly twisting the temporal multiplexing approach to address the measurement of dynamic surfaces. So the way we do is that we actually put the cap1 and cap2 images to have uniform spacing. So that if we assume that there is a phase error of delta between the adjacent cap1 images, and if we also assume that the object is moving with a uniform speed, we can also assume that the error between the cap1 and cap2 is offset by delta over 2 with this uniform speed assumption. So with that, so we actually designed a iterative error correction algorithm. So basically what we did is we separately extract the faces from the cap1 fringe images and the cap2 fringe images separately. And with the delta over 2 being the initial assumption for the phase errors, so we actually did some iterative correction so that if there's up to a point where the phase error is going to be small enough, we're going to output that phase to be our final result. So with that idea, we tested out that algorithm. So here you can see that basically with our algorithm for phase error correction, the 3D result is much better compared to the original one. So basically for the RMS phase error, it's reduced by almost 50%, and the mean error is reduced by more than 80%. So which shows the effectiveness of this error compensation. And we also tested out the algorithm using a more complex object. So here is a sculpture face. So as you can see here, although it's not perfect, still you can observe the improvement of the 3D measurement quality on the sculpture surfaces. So using the proposed method. And we're also proud to say that this paper we got highlighted on the cover page of Optics Express. All right, and up to this point, I have talked about the measurement of shiny surfaces and high-speed moving surfaces. So apart from the research on the high-speed 3D sensing, So we also did some research on the optical metrology for some complex geometries. And for optical metrology, one of the challenge we would encounter is that when we're measuring some objects with abrupt geometric changes, there could be some areas where your projector cannot illuminate. And when your camera sees that, it is going to look like shadows from your camera image showing here. So if this is the case, on the resultant 3D geometry, there could be some information loss. So basically, this could be some problem while we're doing the fine-scale optical metrology for abrupt geometries. And to address that, one of the most efficient way is to basically employ a uniaxial system setup. So here what we do is that basically we put a projector right here and a camera, and they are oriented in 90 degrees. And we will put a beam splitter to make their optical axis to be collimated in a coaxial manner. So basically here, we observe is that if we feed the projector with a binary pattern, so basically we will see that the level of the focus of that binary pattern is directly related to the depth of the object you're measuring. So in other words, so if there's a point, so its level of defocusing of the binary pattern is directly related to how far away it is from the in-focus plane. So observing this phenomenon, we're actually thinking about whether we can directly quantify the depth by identifying what is the level of defocus for the binary pattern. So this is basically what we are trying to do. And basically, if we can quantify the level of defocus, we can directly identify the depth. And if we want to do that, we need to first of all do some inspection for what is actually the quantified relationship between the focus of projection and the depth. So there are a lot of scientists who have done some theoretical derivations for quantifying the relationship between the depth and the projection defocus. And what we can derive is that actually there exists a rational function that can relate this level of defocus with the depth. So if we can quantify the level of defocus of the fringe pattern, we can actually just extract this depth information through an accurate calibration. So if we want to do the depth quantification for the entire object, we have to do a pixel-wise quantification for the level of defocus. And how do we do that? So the idea we do is by employing the phase shifting. So here I'm showing you the basic idea of this approach. So from this fringe image right here, you could see that we're actually moving this fringe by employing some phase shifting. And after doing that, we're extracting the temporal intensity curves for each of the pixel. So this curve will actually give us some indication of how defocused it is. So you'll see that for the curve of the more defocused one, it will be like a much more having a lower peak compared to the one that's more in-focused. So actually for the temporal intensity curve, it can be regarded as a convolution between the square wave with the Gaussian function. So the key to quantify the level of defocus is by extracting the corresponding Gaussian function through a deconvolution. So after deconvoluting that, you can basically identify the key parameter sigma as the quantification for the level of defocus. So with this idea, we actually did some simulations and also the experiments. And with that, we can see that we can well reconstruct the objects with some abrupt geometric discontinuities, including some step height object and deep holes, and also the stacked microscope slices. So for this technology, with a field of view of multi-centimeters by multi-centimeters, we can get an accuracy about 14 micrometers. All right, so apart from some innovations in 3D optical sensing, we're also motivated to explore the applications in different aspects. So the first application we explored is basically the in situ monitoring for the additive manufacturing. So additive manufacturing is right now a pretty hot field, and people are trying to use this to design some complicated geometries. Well, here working with the Remanufacturing Institute in the USA, we're trying to see that whether a special technology called direct energy deposition is able to become a good approach for a repair technology. So for example, here I'm showing you a picture with a machine surface with defects for a engine's cylinder head. So the direct energy deposition is something that you are depositing the layers of metal materials. So intuitively, this can be an approach that can serve as a repair technology for a surface with defects. However, after we are done with the repair technology, so from the micro CT images, we can observe that there are a lot of porosities and cracks inside of it. Then it would be crucial to develop an in situ monitoring approach so that we can do some monitoring to facilitate the possible corrective actions or some decision makings during the process of additive manufacturing. So here is some system we developed inside of this direct energy deposition machine, which can basically scan the layer-wise surface topographies during the manufacturing process. So here I'm showing you examples of a good printing where you can see that the surface textures is basically showing a uniform textures all over the place. But for some examples of bad printing, you could see that the surface topography is going to have some variation from one end to the other. Basically, by the monitoring of the surface topographies, it shows the feasibility of this technology using fringe projection as a valid approach to do some in situ monitoring. So we're still working on this effort, and our ultimate goal is to basically make it to be a reliable approach to facilitate the decision-making in situ. So apart from this technological development, we also did some quality evaluation for the metrology. So I know Professor Richard Leach have done a great talk about the trustworthiness of optical metrology data, and we also did some preliminary research along that route. So what we did is that we just found a high-resolution focus variation microscope as the ground truth geometry, and we also measured using our fringe projection. So we developed a statistical tool to basically serve as the similarity evaluation criteria. So what we can observe here is that by using a function called Pearson's correlations coefficient, basically for surfaces with a similar for the same surface and different surfaces, we can basically have a clear distinction on the quantification of Pearson's correlation coefficient. So this tool can be utilized as a criteria for judging the similarity of shapes in different applications. So if you're interested in knowing the details of this, we have a paper published in Optics and Lasers Engineering. So just in case if you're interested in knowing the mathematical details. And apart from the applications in the metal additive manufacturing, we also tried to do some inspection for civil additive printing. So right now in the civil engineering, so people are trying to do some 3D printing for some large structures, such as the house. So basically what it does is that basically you are going to feed into the 3D printer with some different kinds of materials like concrete, clay, or plasters, so that you're going to have a nozzle to squeeze out the materials and print out the geometry layer by layer. But the problem is that, so for this kind of 3D printing, basically the materials would need some time to solidify. So basically after it's squeezed out from the 3D printer, you're still going to have some deformation afterwards. So that is going to cause some defects. And also, your printed lower layer need to have the ability to uphold the weight of upper layers, which could also cause some problem after the printing. So the civil engineers would actually need some quick inspection tools to just quickly test out the quality of the printing using different recipes of materials, rather than using some visual inspections. So here are some efforts we did. So basically we use the Fringe projection to do the 3D imaging for the geometries of the 3D printed clay samples. And we actually established a protocol with different parameters, such as the variation of layer width, layer thickness, surface angle, cross-sectional area, the outer diameter, and the height. So we can see that for a good printing like the sample 1 right here, its variation is pretty small all across all the parameters, and they are pretty well centered on the contour plots. So actually, we found this is very useful, and it can replace the current visual inspection by civil engineers, and we can now have a way to record and basically quantify the quality using the 3D data. And apart from the 3D printing, we also collaborate with civil engineers by inspecting the particle size and shapes for the soils. And for civil engineers, basically the size and shapes for particles inside of the soil is very important. And it is going to decide something like the packing density and the strength and the compressibility of the soil. So right now, what civil engineer is doing is that they are using some manual testing like sievings and also some calipers to measure the size and shapes of the soil. So right now, we try to do the Fringe projection to basically quantify the shape and size of the particles. And we can see that it agrees perfectly with the manual testing, and we can claim this is a reliable indicator for the shape and size of the soil particles. And we actually got this paper highlighted on the cover page of Geotechnical Letters in 2019. Okay, to make a quick summary of what we have done, we've done some innovations in 3D optical sensing, including the shiny surface measurement, dynamic surface measurement, and uniaxial 3D sensing. And we've also talked about some applications, including the in situ monitoring for additive manufacturing and some civil engineering applications. And lastly, I want to thank my research team. They are all excellent graduate students, and especially Mr. Yi Jun and Mr. Vignesh Suresh, who are the major contributors to the work I presented today. And also, I would like to, so everybody is welcome to visit Iowa State if you have time. And we have actually one of the most beautiful campus towns in the entire United States. And now, so just time for questions, and thank you very much.
Okay, thank you. Thank you, Dr. Lee. And thank you for your wonderful presentation. I got 2 questions from audience. The first one is, in your first research work, there are, the phase shifting or several recorded branch pattern. For each pixel, there are 6 or more great scale value. How to decision which one is the best for the phase and shape retrieval? Okay, this is the first question.
Yeah, so this is a very good question. So the way we determine which one we're going to select is by calculating the contrast of the fringe image. So basically, first of all, if it is not saturated and if it has the highest contrast among all, we are going to select that corresponding pixel. So that is my answer.
Yeah, thank you. The second one is for the third research work on uniaxial 3D metal. Does it, usually we take the project and the camera from different angle to record the fringe pattern. And in your setup, maybe the projector and camera axis is is a coincide or the same way. How to retravel the phase information and finally reconstruct the 3D shape. Okay.
Okay, thanks for the question again. And actually here we did not use the phase at all. So the way we reconstruct the 3D is by basically getting this intensity curve through the phase shifting. And we did a deconvolution to identify the corresponding Gaussian smooth, the corresponding Gaussian smooth function. And after getting the Gaussian smooth function, we extract the sigma parameter from the Gaussian. And that sigma parameter is how we quantify the level of defocus. And the way we get depth is by directly finding out the depth throughout this rational function. So if we get the sigma using this function, we can get the depth d right here. So hope that answers the question.
Okay, thank you. I got it. And thank you. Due to the time limitation, I want to close this section. For more further detailed information, all the audience can find the two speakers' contact information to get some further discussion or further information. Thank you. Thank you, the two invited speakers, Dr. Huang and Dr. Li, and thank for the audience for your attention. And
okay, many thanks.
Okay. Yeah. Thank you. Bye.